students. So today we'll go for the next concept, that is the initial reaction. Initial reaction. So what is this initial means? So this initial is nothing but reverse of acid hydrolysis. Okay, this is a reverse of acid hydrolysis. This is the reverse of acid hydrolysis, where one of the anion is going to replace the aqua ligand H2O from the coordination sphere. For example, I will take this example: CO NH3 5O H2O, okay, plus 3 plus X minus. Okay, so what I will get here now? CO NH3 5OX plus H2O. So here one of the aqua ligand H2O is been replaced by the anion here. So such a reaction we call it as a initial reaction. Okay, we call it as a initial. This is called initial reaction. See, so one of the anion here, okay, is replacing H2O from the coordinated sphere, and this reaction we call it as a initial reaction. Okay, it's the reverse of the hydrolysis, acid hydrolysis. Okay, and if you see the rate of reaction, it depends on the complex as well. It depends on the concentration of the ligand anion. So this is okay. So that's why it is a bimolecular reaction. So this is a type of bimolecular reaction. Is it right? So this is what the initial. So what about the metal to ligand bond here now? So we will learn what happens to what will be the metal to ligand bond here. Is it right? So nature of metal to ligand bond. So what will, whether they are going to be detached from the metal of aqua bond H2O, okay, or not? This we will learn here by taking an example of the anion, that is nitrate, NO2 minus. For example, if I take this now, NH3 okay, so water plus 3. If I treat with this now, this anion NO2 minus. So what I will get here now? So I am going to get here that nitrate is going to replace this H2O, and I am going to get here, what is that? CO NH3 nitrite complex plus water molecule will be here. So I am going to get nitrite complex. This is which complex? Nitrite ONO. Now the question comes here that cobalt to oxygen of this aqua, whether it is being replaced, attached, or directly NO2 is linked with this complex. This how to know here. So metal to ligand here, metal to ligand here, whether the bond is being cut off or not. How to know? By labeling. So what we can do here? So cobalt, or we'll go for like this here to know this NH3 COOH2 here. Like this we can go here to know whether this cobalt to oxygen from water ligand is detached. Okay, when we treat with this NO2 minus. So we have found, so I will label here like 18, oxygen 18 I have labeled here. So when I treat this, okay, so with nitrate ligand, what I have seen is I got this complex CO, or I will take reverse meaning here, NH3 pentamine 5 COO NO plus 2 plus water molecule again here Cl. So I have got this labeled oxygen as it is. So that shows what now? That shows that metal to ligands, cobalt to oxygen in this is not broken, it is intact. Okay, the bond here is intact here, so it is intact. So that's why, so this remains intact. This bond CO and O is remained intact. That's why this is the best example to show that the metal to ligand here, the bond remains intact by labeling, and whatever the anion is in replacing this H2O is not detaching this totally, is not breaking this bond totally. So this is what about the initial, brief introductory and the simple reactions based on the initial. So I think here we completed the first part of the unit 2. Now next we go for the biomnemonic concepts. So next part will go for the bioinorganic. So in bioinorganic, so you are having the storage and transport of oxygen here. Okay, the first part you are having storage and transport. Storage and transport of dioxygen. Storage and transport of dioxygen is done by whom? Hemoglobin. Okay, in this one, in body system, it is done by hemoglobin. It is done by hemoglobin and myoglobin. It is done by hemoglobin and myoglobin. So oxygen is transported by the hemoglobin and it is stored by the myoglobin. Okay, hemoglobin, how many units is having? It is made up of 4 heme units. It is made up of 4 heme units, and myoglobin is monomer. It is a monomer. So it is made up of how many? So 1 heme unit. Is it right? So this is what the difference between hemoglobin and myoglobin. And hemoglobin has around 64,500 Dalton. Molecular weight of hemoglobin is 64,500 Dalton. Okay, and it is made up of 4 heme. Okay, 4 heme means what? From the iron, like this. So this is 1. This is 2. So afterwards we will see here. Then this is iron 3, and this is iron. Again one more branching. That is like this. So this is how, like this. Okay, 4 subunits. So hemoglobin is made up of 4 subunits here, and they are joined by what? They are joined by, so it is around 141 amino acids here. And here you can see around 146 amino acids. 146 amino acids, and they are joined by here electrostatic. They are joined by electrostatic bonds of NH3 plus and COO minus. Okay, so they are bound by the electrostatic bonds of NH3 plus and CO minus. So this is how we can show the structure of the hemoglobin. Is it right? So how does this bind? Or during binding of the oxygen here by the hemoglobin, the oxidation state remains same here. So I will draw a structure of hemoglobin here, which is having the porphyrin ring. So this is what the hemoglobin structure will be. It has been coordinated here by one of the bond here, like this. Okay, so this is nitrogen of midazoline. Okay, now you can go with the bond here, double bonds. Like this. Okay. So totally, you have to see that it should have so 9 double bonds. Okay, so it will have around 11, I think. So you have the 11 double bonds. 11 double bonds you have to see here in this porphyrin. This is what nitrogen of porphyrin ring. So here you can see here. So this is the nitrogen of porphyrin ring. This is a porphyrin ring. This is your hemoglobin, and it is made up of porphyrin ring here, so of nitrogen, and this imidazole here. Okay, and this is which one? This is deoxyhemoglobin. This is a deoxyhemoglobin, which is 5 coordinated. So it is a 5 coordinated, and if you see the geometry here, so it is made up of what? Square pyramid. So geometry here is a square pyramid. Okay, 5 coordinated, so 5 square pyramid, and iron is in state +2 state but high speed. So iron here is in high spin. So high spin means what? So it is not in the plane, high spin. That's why this is called as tensed state, T state. We call it as the T state of the hemoglobin, that is tensed state. So this is a tensed state of the hemoglobin, and it is in high state. High state means what? Now if you see D6 system, iron is in D6 system, and it splits into what? Now T2G, Eg, 1, 2, 3, 4, 5, 6, like this. Okay, high speed. Is it right? So this is how, and here the electron is in Tx square minus y square, dx square minus y square. And high speed, you can see here, you are having some 4 around unpaired electrons here, so 2, 3, 4 here. So that's why their ESR active. So this compound is ESR active. This compound is ESR active. So it is going to show the electron spin resonance because of the unpaired electrons. Now what happens when this reacts with oxygen now? What happens when this reacts with oxygen? The same thing I will draw here. Nitrogen. So you can draw here by drawing and see that right, okay. So you can draw this conjugated bond and see that there should not be conjugation should be there and 11 conjugated bond should be there. Now what will happen down here? So this is nitrogen of imidazole. This is bromine protein attached with histidine. Okay. Bromine protein attached by histidine. Okay, and what will happen now here? Oxygen will bind here like this. Okay, now it becomes oxyhemoglobin. This is called as oxyhemoglobin. See, and here bond is made up of 130 degrees. So this oxygen after binding, it will make a bond of 130 like this. So what about this is quite opposite of this? This is inactive. ESR inactive. Why? Because the iron here also is in +2 state but low spin here. Okay, iron is in low spin here. So D6 system. So I can split here like this. So TQG, TG, 1, 2, 3, 4, 5, 6. Since it is low spin here, so their ESR inactive. So this oxyhemoglobin is ESR inactive. This is ESR inactive, and this is what oxygen here. It is bounded to the 6th coordinate here. The 6th coordinated. So here 5th coordinated. This is 6th coordinated. Okay. So what will be the geometry here? So if I draw like this. So like this, if I draw like this, it becomes which geometry? It is an octahedral geometry. So this will show octahedral geometry. So this will show your oxyhemoglobin shows the octahedral geometry here. Okay, and this is ESR inactive, and here the oxygen is bound in the form of superoxide O2 minus. Okay, O2 minus. So this is how. Okay, and how it is known? It is known from the IR spectroscopy. Okay, from the IR spectroscopy and XRD. Okay, so from XRD, okay, and IR. So this bond angles and the binding is being found out here. Okay, so if you see the stretching frequency here. So just practice this bonding of deoxy hemoglobin and oxyhemoglobin, and you can have some differences as I said here. Okay, so 11 bonds you can make it here, and some of the and this like here T state, that is tensed state I said. So oxyhemoglobin is R state. We call it as a R state. R means what? Relax. Okay, relaxed. That means what here? The iron is perfectly fit into the plane here, but in here the iron is not exactly fit into the plane. It is out of plane. We will see that also. So this is how some of the difference between the deoxyhemoglobin and oxyhemoglobin bond angle and ESR active, then geometry of this. So this is what some of the difference and the binding here, O2 minus. So oxygen is bound for this hemoglobin in the form of superoxide, that is O2 minus. So next we go for mode of binding. Okay. So mode of binding. What are the mode of binding of oxygen here? So you can see oxygen O2 minus, O2 and minus 2. So this is mode of binding. I can say mode of binding. Okay. So mode of binding here. So this is what how to know this mode of binding. So we can know this from the bond order. So you know that bond order. So bond order of oxygen is how many? How much? It is 2, and this is 1.5, and this is 1. Okay, bond order of peroxide. This is a peroxide. Okay, this is superoxide. Okay, and this is your dioxygen. This is your dioxygen. Okay, and the bond order is like this. When bond order is like this, what will be the frequency here? So per centimeter. New frequency. Frequency of IR will be what here? So you can see here it is around per centimeter 1500, 10 per centimeter. This is around like this. Superoxide 1150 per centimeter around, and this will come around 850 to 700 per centimeter. This is the frequency. Is it right? And if you see the IR and Raman stretching, IR and Raman stretching frequency, IR and Raman stretching frequency of oxyhemoglobin, it comes to be around like 1106 per centimeter, and deoxyhemoglobin or oxyhemoglobin, it comes to be around 1103 per centimeter. It's not so much difference between these two. So almost 3.03 per centimeter difference is there. So this is how we can make the stretching frequency as well as the different mode of the binding, how they bind to the oxygen. Dioxygen is going to bind to the hemoglobin. Is it right? So they are made up of 4 hemes. Okay, and that's why we say that it is a cooperative binding. Okay, so we say that this is a cooperative binding. Hemoglobin shows cooperative binding, while myoglobin is non-cooperative. So what does this mean, cooperative binding now? Cooperative binding. So what does this mean, cooperative binding now? See here, in simple if I go, now same hemoglobin I can write in this way. Okay, you take it here like this. Okay, this is a globin protein. This is how. Okay, and this is what now, deoxy. So in deoxy, what I said, iron is out of plane. So what we can show this iron out of plane here, so like this. Here we can show like this. Okay, like this we can show. So this is out of plane here from the center, and it is around 70 picometers. Okay, the distance of iron to here is 70 picometers. That's why it's called tensor. It is called as tensor. The iron is out of the plane here in deoxy. Deoxy. When it reacts with oxygen, what will happen now? Now iron will fit into this like this. This is nitrogen. This is mid-globin protein. Now it is going to fit here, and oxygen is going to bind here like this. Okay, so this is what I can take it as a A1. Okay, similarly, if I go for now next A2, what will happen now? So it will react with another oxygen to form another this one like this. Nitrogen of globin protein, histidine. Okay, and here you say like this, and this is of 2 like this. See, like this 2. Is it right? So second, like this, it has 4 hemes, so it is going to bind with 4. That is the A1, A2, A3, A4, where the equilibrium constant will be A4 greater than A3 greater than A2, then A1 like this. Is it right? And this mode of binding we call it as cooperative mode of binding of hemoglobin. Like this we can do here. So Hb plus O2 will bind HbO2. This is for A1. Similarly, HbO2 will bind with another O2, giving you HbO2 twice. Next, HbO2 twice will bind with another O2. This is A2. This is A3. Will give you HbO2 thrice. Similarly, K4 HbO2 thrice plus O2 will bind you HbO2 4 times. See here. So where Hb is 1, 2, 3. Okay, 1, 2, 3, 4 times like this. Is it right? So this type of mode of binding we call it as a cooperative binding. We call it as a cooperative binding of the hemoglobin. And this is red in color, you know. So this is red in color. Why? It is because of intra-ligand transfer, electron transfer. This is because of intravalence. Okay, electron transfer, that is pi to pi star. Pi to pi star transition is there in this, and that's why this is seen to be red in color. Is it right? So I think this is more than sufficient for today's video here. So today what we learned regarding the ionization reaction. What do you mean by ionization reaction? And finally we started with the new concept of bioeconomic, that is mode of binding and storage of the oxygen, dioxygen. So that is what about the hemoglobin and myoglobin. So myoglobin is monomeric in nature, and hemoglobin is quaternary. That means it's having the 4 heme units with salt bridges, binding with the salt bridge of NH3 plus U minus, and you have seen that how they bind for the oxygen and how the mode of the oxygen binding and the difference between oxyhemoglobin, deoxyhemoglobin followed by the cooperative binding. What do you mean by cooperative binding of the oxygen shown by the hemoglobin? No doubt it is going to show pH effect as well as Bohr effect, which we will study in the next video. Hope you have understood this today's class. So thank you. Have a nice day.